Hello everyone, and welcome back to Mitchell's Physics Review. Today we are looking at the Biot-Savart law. Let's take a look at our problem. Two coplanar and concentric circular loops of wire carry currents of I1, which equals 5.6 amps, and I2, which equals 2.3 amps, in opposite directions as in the figure below. Let R1 equal 12 centimeters and R2 equal 8.8 centimeters. Let's start by listing our givens. I1 is equal to 5.6 amps, I2 is equal to 2.3 amps, R1 is equal to 0.12 meters, and R2 is equal to 0.088 meters. We also have N is equal to 1. Now, how do we know this? N represents the number of coils in the field we're trying to look for. So since these are each one singular coil, we know that N is just equal to 1. Next, we can determine the direction, as you can see by my little diagrams down here. We can start with current 1, or the loop that current 1 is running through. We have it running in a clockwise direction. So if we use the right-hand rule and put our thumb in the direction of the current and see which ways our fingers are pointing, they should be pointing inwards or into the page. Similarly for I2, it's going in a counterclockwise direction, so we once again use the right hand rule, put our thumb in the direction of the current and which way our fingers are pointing, and they should be pointing out of the page. So the direction of B1 should be inwards or into the page, and the direction of B2 should be outwards or out of the page. Now that we have identified the directions of the magnetic field and we've taken a look at our givens, we can start with part A. What is the magnitude and the net magnetic field at the center of two loops? So to start, we're going to use the equation magnetic field, or B, is equal to mu naught times the current over 2R times N, or the number of coils. Since we know N is just 1, this will pretty much drop out of the equation. From there, we can write an equation for both B1 and B2. For B1, we have mu naught times current 1 over 2 of radius 1. And for B2, we have mu naught times current 2 over 2 times radius 2. We can then plug in our given currents and our given distances, or radiuses, along with the constant mu naught for both B1 and B2. From there, we can solve for the magnitudes of B1 and B2. So B1 should equal to 2.932 times 10 to the negative 5th Teslas, and B2 should equal to 1.642 times 10 to the negative 5th Teslas. But as you might have already caught on, how are these both positive if the current's moving in a different direction? Well, they shouldn't both be positive. So from there, we're going off of our coordinate axes and what we call to be positive. So we're going to say B1 is negative 2.932 times 10 to the negative 5th Teslas because it is going into the page. And usually for standard coordinate axes, into the page is the negative z direction and out of the page is the positive z direction. So then, for the net B, we have is equal to B2 minus B1, taking into account this negative. We can plug in our values for B2 and B1, and we find that the net B is equal to negative 1.29 times 10 to the negative 5th Teslas, or 12.9 microteslas. Now, once again, you might think that I've skipped a step and how we got this negative to go away. Just remember, for part A, we're only looking for the magnitude. For part B, we are now going to find the direction. What is the direction of the net magnetic field at the center of the two loops? Well, since once again we're going off of a standard coordinate axes, since we would have a net B of negative 12.9 microteslas if we're including the direction, not just the magnitude, we know the direction is into the page. How do we know this? Well, once again, in our standard coordinate axes, we said negative was into a page. So if our net answer of the magnetic field was negative, we know that the net direction was into the page. Finally, let's take a look at part C. Let R1 remain fixed at 12 centimeters and let R2 be a variable. Determine the value of R2 such that the net field at the center of the loop is 0. So how we can start part C is by saying the net field, or net B, is equal to B1 minus B2, like we did before. Then we can say the net field is equal to 0, as the problem told us it should be. Then we can say that B1 is equal to B2. From there, we can plug in the equations we found earlier for B1 and B2 and cancel out like terms. From there, we get I1 over R1 is equal to I2 over R2. We can rewrite this to solve for R2. So we get R2 is equal to current 2 times radius 1 over current 1. We plug in all of our givens and the fixed value of the radius for R1, and we get 0.049 meters. And once we convert, we get 4.9 centimeters. Overall, the biggest thing I struggled with was making sure to remember this negative from part A on the magnetic field 1. I forgot that since it was, even though it was asking for magnitude, we still had to take into account this negative to find the net magnetic field. I hope this video helped a lot, as it did me. Have a great day.